All right, guys, let's do a little review problem from that last section before we get into chapter 5. So that's section 4.3. So let's say that 81% of Americans tired of hearing about the wall. So I start talking about it. Alright. So I try to stay out of the political part and just say, I don't care how you feel about it. You're probably tired of hearing about it. Or you're part of the 19% that want, tell us how more about it. So let's say I pick, what you got, Jeff? 37 murders. What's the probability that exactly, what you got, Jeff? Let's say exactly 29 are tired of hearing about the wall. So what important parts of this problem can you pull out? Important parts of the problem, pull out. Yeah, you know P and Q. I like it. So P is what? Not the idea of it, but what is it? Yeah, because it is probably a success. Tired. I'm looking for tired. You're poor. You're weak. You're tired. Q. Yeah, the rest. Very quick side note. All right? Completely side note. If you have to do, this happens so many times. Let me just do this. 1 minus 0.4, 8, 2, 9. I know you got a calculator. Just let me show you something. Let me show you something. Make these 9. What makes this 9? 5. What makes this 9? 1. What makes this 9? 7. And what makes this 10? That's what it is. And the reason that is for example, you guys get the idea? Let me do another example. 1 minus 0.2, 8, 5, 3. 7 makes that 9. 1 makes that 9. 4 makes that 9. 7 makes that 10.
Oh, it's always 9 and 10.
Yeah, and if you think about it, why does that make sense? Because if you add these and that's 10, it's going to carry over. That's going to make that 9, 10. It's going to carry over. How does you make that 9, 10 if you carry over? How do you make that 9, 10? It's a beautiful little shortcut. I know you're like, I got a thing that'll do that shit for me, Mr. Waller. But we're humans. We created numbers. We probably should be able to play with them, right? Just it happens often enough. It's a cool little quick thing you can do. Or not. It's your choice. Okay, so here it'd be 1 makes that 9 and 9 makes that 10. Okay, what else can I get from this? 37 is what? N. That's my total number. And what's X?
29.
29. That's the number of successes that I want. It's never going to be 29 out of 37. That doesn't make sense. That would only make sense if it was all equally likely. But no, it's more likely that they are tired than they're not tired, right? So you can't just do 29 divided by 37. That doesn't mean anything. Doesn't mean anything. So X is 29. So how do I set this sucker up? The probability. What's the formula for this? Oh, shit. I got to start at N. This is the weird little part, the rest, right? Q to the rest. You don't even have to be honest, this is another example of how the formula's job is difficult. It has to show you everything that could possibly happen. So sometimes it's actually harder to use the formula. We know that from probability. If I start to set this up, I got 37 people. I want to choose 29 of them to do something. So I got 29 of these. So how many of these do I have? I think I heard it. 8, the rest. Those exponents always have to equal the total because you're breaking them into 2 groups. And then throw the old calculator. Let's see if we get the same answer. Okay, I got an answer.
I think of the P, but is that a Q or like
That's a Q. P and Q, right? Yeah. 1, 4, 5, 5. I like it. So just under a 15% chance that out of a group of 37, there would be 29 who are tired of hearing it. Okay. All right, that's enough of that. So that's section 4.3. We went over last time, just a quick review problem. Those are, if you let it be, it kind of sets itself up. I know it's kind of repetitive, but it's kind of nice. I got this many people, choose this many to do this. So the rest do this. Throw in the old calculator. Okay. So, moving on. The chapter 4, let's see if you guys get this. Chapter 4 started with this kind of stuff, right? And then we got to binomial, which is all about 7 people liking something out of 80 or whatever, right? So what kind of data? Oh, shit. True. Continuous or discrete? Discrete, because we're talking about people, and here we got 0 TVs, 1 TV, 2 TVs. So chapter 4 is really all about discrete probability distributions. What's the title of chapter 5?
continuous?
No, what? All right, so now we're going to get into, so this is discrete. Why? Because the data has to be whole numbers. You can't have 4.73 successes. That's weird, right? So this is going to be about continuous distributions. So the most classic example of the first kind of distribution is called a uniform distribution. Let's say we're in Germany, where they're a little better with schedules. So we're not in Italy, which is like, it's 2 hours late. Oh, that's no big deal. And you're waiting for a bus, and the bus comes every 15 minutes. So when you get to the bus stop, and the bus is there, how long did you have to wait? 0 minutes. You can wait anywhere from 0 minutes, but when you get to the bus stop and it's just pulling away, how much do you have to wait? 15. Now, when could you get to the bus stop? It could have just pulled away, or it could have pulled away 3.746992 seconds ago, or it could have pulled away 3.4897 minutes ago, or it could have, So you could wait anywhere from 0 to 15 without skipping any values. It just depends on the moment you step in the bus stop. However long it took when it left is minus 15 is going to be how long you have to wait for it to come back. So there's no time that's more likely than any other time. It's uniformly distributed. It doesn't look like this. There's nothing that's more likely than anybody else. There's no reason you would just always get there right on the bus. Even if you feel like you're a lucky person, that just means that you focus on the good things, to be honest. That's the interesting thing about it. You feel like you're lucky, you just remember the good stuff. So it's going to look like this. That's the distribution. So it's not normally distributed, right? It's uniformly distributed. Now here's what's interesting. All right. Does that by itself make sense? This is always interesting how I want to get into this. Bless you. Quick side note about stuff here. Anybody played darts? Yeah? You know, I've had a dartboard before, and the wall had more nicks in it, but if you, so it basically looks like this, little pizza slices all around. I'm not going to draw the whole thing. Drive me crazy. Everybody understands the dartboard, the bullseye, right? So everybody know? So let's say you're just blind, you're just throwing them, not even really trying, and you only count the ones that hit the board. The probability that I get it right here. Think about how this makes sense. This would be really difficult to make you come to this conclusion yourself, but it's related to the area of that thing, right? You guys with me? So if the area of this little circle, let's say it's 5% the area of the whole circle. Just to say something. So what's the probability that if you count only the darts that hit on the board, that what percentage of your darts are going to hit there? 5%. Does that make sense? What's the probability it's going to hit this area here? Well, that's much bigger. Let's say that's like 40% of the total area. So what's probably going to get darts in here? 40% chance. Because what are we considering? What's the probability, if I only count darts that hit the board, what's the probability that I get darts that hit the board? 100% because it's the whole thing. So here's the really cool thing. If you give a visual, a graphical representation of the situation, all the probabilities are equal to the areas. What the shit do I mean? Okay. First thing is, how do I make the area of this rectangle 1? I have to start there, because if I make the area of the whole thing 1, then the little areas of everything in between would equal the probability. Why did this work? Because I consider the whole thing to be 100%, 1. So how tall would this have to be? So the area of this rectangle is 1. How wide is this rectangle? 15. And how do I get the area of a rectangle? Yeah, so it'd be length times width. We'll say height, because we're going to stand that sucker up. So it'd be like base times height. Is that cool? So 15 times what is 1? Yeah, that's the idea of a reciprocal. That's what they do. Do you guys see that? It's not 1/15 because that's 15. What if I had a rectangle look like this? How tall would that one be? Yeah, it's the width is 12, so the height's got to be 1 over that. Let me stop here for a minute. You guys see that?
Wait, is that 12 now?
How wide is it?
I don't know what that number is.
Oh, well, okay.
15.
So how wide is it? 12.
Oh, minus.
So this is 112. So be careful. Whenever I pick a 0, which is related to the physical situation I'm in, people focus on, oh, it's always 1 over that number. No, it's 1 over the width, right? That makes sense, because the area is this times this. If this is A and this is 1 over A, those multiply to be 1. So watch this. This only works for, let me be careful. This works for everything. This works for everything. If I can graph the situation like we have a normal curve, and I consider the whole thing to be 1, then any probabilities questions would be related to the area. So what do I mean by that? What if I said, what's the probability? So let me take this other one away. That rectangle is not related to our bus problem. If I said, what's the probability I have to wait? Green. You suck, green. Go away. Go away. What's probably I got to wait? What do you got, Jeff? 8 up to 11. Have you all drawn this on your notes? So can you put that in there? Put 8 to 11 in there. So it'll be roughly here to there. It doesn't really matter. You don't have to be perfect. So what's the area? that represents this problem, right? This area right here, this represents that problem. What's the area of that rectangle? What's the area? How wide is it?
88.
How wide is it?
Oh,
3. How tall is it? They're all 1/15th, right? So the probability that it's between 8 and 11 minutes will be 3 out of 15, which is 20%. So if there's a bus that always comes every 15 minutes, then the probability you get there and have to wait from 8 to 11 minutes is 20%. It's almost too good of a thing that if you represent a probability distribution visually, the answer to a probability question is the area related to that question. That's beautiful, and the dartboard thing really hammers it home. Just like throwing, not even trying, throw, and only count the ones at the dartboard. The probability you get somewhere is related to the area of that place. And the crowd goes, whatever, man. Okay, so please, dear God, uniform distributions are finding areas of rectangles. All right, so let's try. Let me let you guys try one. All right. So given a uniform distribution from 7 to 35, right? Part A is graph indicating height, like that. And then part B is find the probability that it's between 10 and 21. Go. It's just a bunch of rectangles. Pretend like that's a straight line. How tall is it? Yeah, 1/28. I like it. That's what makes the whole thing become 1, and that's why it's a valid probability distribution, because all the probabilities add to 1. And then you can just use what you just did. Here's 10. Here's 21. So what's the probability I'm in that purple area? So how wide is it? And how tall is it? So 11/28, which is whatever the hell it is.